In this video, we're going to work one last moment of inertia problem by integration. We're going to find Ix, Iy, and Ixy. And then I'm actually going to use those to find the Imax and Imin and the orientation or the angle of Imax and Imin. So we're looking ahead to material that we're going to do here soon. But again, just looking ahead and showing you that. And then we're going to circle back to another problem that we integrated for and at least show you the transformed coordinate system for Imax and Imin. So this is an area bounded by this curve y is equal to 1 over 32 x cubed. And the x coordinate is 4 inches. The y coordinate is 2 inches. This Imax and Imin, I'll explain those in a moment, and this theta p, I'll explain that in a moment. So basically for this area, we're going to find the area, which I think I probably did this just to practice setting up the integral. And so just choosing a dA, dy, dx, integrating y from 0 to 1 over 32 x cubed, and integrating x from 0 to 4. The area actually is 2 square inches. Ix is the same integral, except now we put a y squared in there. And Ix is 1.067 inches to the fourth. Iy is the same integral setup, except we put an x squared in there. And we integrate, and Iy is 21.33 inches to the fourth. And Ixy is the integral of xy dA. It's the same integral. We put an xy in there, and we get Ixy is 4 inches to the fourth. Polar moment of inertia is equal to Ix plus Iy, which is 22.4 inches to the fourth. And we also found radius of gyration, Kx and Ky, as we explained earlier. But now we're going to take the Ix, the Iy, and the Ixy, and we're going to find the rotated coordinate system at which there's an Imin and there's an Imax. And these formulas we're going to develop here very soon. But again, I'm looking forward to show you why, one of the reasons why we're finding Ix, Iy, and Ixy. So the formulas we're going to use is the Imax and Imin. The formula for that is Ix plus Iy divided by 2, plus or minus the square root of Ix minus Iy over 2 squared, plus Ixy squared. And so this is basically an I average term, plus or minus this term. So this is the average of Ix and Iy, which is 11.2. And then this term is 10.89. Actually, when we get to Mohr circle, which you may have heard of, this is the center of Mohr circle, and this is actually the radius of Mohr circle. So our Imax and Imin are 22.1 inches to the fourth, and that's our Imax is 22.1 inches to the fourth, and our Imin is 0.306 inches to the fourth. We're interested in what the orientation of those guys are. And so we have a formula for theta p. And so theta p is an angle to a principal moment of inertia. It's measured from the x-axis, and it takes you to the closest principal. And by principal, I mean either the Imax or the Imin. And so if you take our Ixy, which is 4, and plug that in here, our Ix is 1.07, our Iy is 21.33, plug them in here. That's 2 theta p is the inverse tangent of this guy. And we get theta p is 10.8 degrees. And so our nearest principal to our x orientation is 10.8 degrees up. And so we actually go in here and draw this. So 10.8 inches up. And 90 degrees from that is this other axis. And so if you had a Moore circle, you could tell what that 10.8 degrees you could tell it was taking you to Imin or Imax. Or you could plug that 10.8 degrees into a transformation equation, which would give you Imin or Imax. But in this case, we're just by inspecting the coordinate system, 10.8 degrees takes us to an axis that crosses through this area. And because this axis bisects the area, you know that that's going to be a small value of moment of inertia. And so that must be the Imin. And then by definition, the Imax is 90 degrees from the Imin axis. And so that's the Imin axis. Again, this is looking ahead. We haven't done this yet. We haven't done these equations yet, but we're finding Ix, Iy, Ixy, and I just wanted to show you, how to use those to get these principal values in the principal orientation. Earlier, we actually worked at the Hibbeler problem example 10.2, and we found Ix, Iy, and Ixy is this problem here. And so the Ix, we found 106.7. The Iy, we found 57.1. And Ixy, we found that to be 66.7 times 10 to the 6 millimeters to the fourth. And so if we take all of those values, I didn't show you this before. So we take all of those values that we found, we plug them into the principal angle equation. Again, we'll show this to you soon. And we get a theta p is equal to negative 34.8 degrees. And again, this is the angle from our x orientation to the nearest principal axis, either Imax or Imin. And so we get negative 34.8. And so if you rotate the coordinate system down to that, and then 90 degrees to that is the other principal axis. It's pretty easy. Again, in the when we get to Moore circle, or if we get to the transformation equations, you can plug this angle into the transformation equations to show you whether it's Imin or Imax, or you can use Moore circle at this angle to see clearly that you're at an Imax or Imin. But in our case, you can just tell by looking at it that once we draw this rotated set of axes, because this axis crosses through the area, that has to be the Imin because the area is close to that axis. And then 90 degrees from that, by definition, is the Imax. And so about this Imax axis is a maximum area moment of inertia for this particular area. This concludes our section and our multiple examples of area moments of inertia by integration.